Hello community! A brief history of of AI. You know, we all started with GPT-3. It was a simple model with a text input, a text output. It was trained on patterns. It was trained on speech pattern, on our language pattern. And it had kind of averaged here the internet knowledge and kind of behaved like an average, simplified human. It was just a tiny little knowledge cluster, if you want, in complete isolation. An experiment started here to connect it to the internet. Now with GPT-4 it changed. We had suddenly text and image input and text and image output. So we had our large language model and our vision language model. So we had multiple kind of knowledges here, visual and textual knowledge. And we think the architecture of the system is a mixture of experts. Now, what's new were function calling here for internet access and database access. Plus, we had a structured output suddenly, maybe with JSON. And then we started to fine-tune these models, these pre-trained models here, on our specific training dataset. However, if we could not afford the fine-tuning because it was too expensive, then we had in-context learning example in the prompt or a complete prompt engineering. Later then it changed when we added here reinforcement learning by human feedback, for example. This is what made those open AI models so famous. So we had a pre-trained model, a fine-tuned model, and then we're in the alignment phase. In this reinforced learning, you had at the beginning a PPO, then a DPO algorithm. We forced the system to behave in a particular way that we wanted the system to behave, to be friendly, not to talk about certain topics, and you know what I mean. Now there was a problem right from the beginning because whatever we put in our prompt, the system hallucinated. And the system was trained on data that were about 1 year old because it took about 6 to 8 months to run this complete system on a cluster on Microsoft hardware. So the idea of a function call was now something beautiful, because now if we had a prompt, a query by the user, and the system had no answer, it could just make a function call and ask for help. Well, it called the internet, it called corporate databases, it had access to whatever knowledge was already encoded and available was suddenly accessible. But in the early days there was also a confusion about here the format of the data, because they used here also a sentence transformer to convert here the data into a very particular representation. And they used here a vector space representation with the special feature that semantic similar sentences were represented close by in this embedded representation. So similar topics were clustering in this particular vector space, making it very simple and very fast for a search algorithm if we had a query vector to find here just in the vicinity in our high-dimensional 1000-dimensional vector space here all other entries, all other vectors that hopefully provided the answer to us. So thereby we got now external data, particular for the query, that we could provide now for the system as additional data. Unfortunately, in the early days, all that was returned were irrelevant data, and it was quite a failure. And you had to be lucky to get the right answer. Yeah? But research continues, and with the introduction of re-ranking, the situation improved significantly. Why? Because we had now, this is an AI system, now a third AI system here integrated. And this AI system just said, okay, give me your 2000 best results from the vector space. So everything that is close here to our query vector, all the other 2000 vectors, and I, in my AI intelligence, I'm now trained particular for here this embedding, this vector embedding, and I will give you then, after a mathematical re-ranking, that I calculate this again, the top 3 or the top 5 or the top 10 results. And then this improved, and then 10 results went back into the prompt as a possible solution to the query. And the system had more data to work with. Also the latest data, if For example, on the internet, something was just updated minutes ago. However, and you know the whole system here, you know under RAG, Retrieval Augmented Generation, it did not help with the hallucination. It was the big hope that if we have RAG data, now hallucination would be gone. It turned out no way. But we achieved at least 50% what we set out to achieve. We had the latest data in our data stream. Great. Now, supervised fine-tuning turned out to be also not as easy as we thought. Because if we had a particular domain, like physics or mathematics or medicine, in our pre-trained data set, and then suddenly we had a complete different domain in our supervised fine-tuning, we had problems. This supervised fine-tuning was not really working, and we had a lot more of those beautiful hallucinations. So, careful, supervised fine-tuning, do not cross the domain border. Stay within physics, mathematics, wherever is your domain that you have already trained the system on. Later on, there was a new development, a new trend that we said, okay, if supervised fine-tuning is so expansive, maybe we don't even have access to the weight structures, to the tensor structures, to be able to have a fine-tuning algorithm on the GPU cluster. In-context learning became famous, and we put in our prompt multiple examples of what our task should be like and should be solved like. Plus, we had now access to synthetic data sets from other AI systems, where AI system generated synthetic data for training other AI systems, especially for the reinforcement learning and their alignment phase. And this could include strictly formal limitation, strictly structural limitation. Whatever we wanted the system to behave, suddenly we were able here to input this. But of course, as you remember, here's an AI system, here we have kind of an AI system, then here maybe we have another AI system. Every AI system was hallucinating, so you got an idea. Well, this was not really the optimal configuration for us. And especially then, if later we had then code LLMs, as we called them at the time. So we had our large language model, we had the vision language model, and then we had the code LLMs. Things become quite complicated because, as I told you, these were domain-specific training data for speech, image, and code, and it got really, really complicated to have here the optimal training process from the pre-training fine-tuning, and then in the alignment phase that you really cover here all the different particularities of the system. Plus, somebody said, hey, maybe the transformer architecture itself is not the best solution because it had a quadratic complexity and a compute complexity. And some people look back in the literature, found that we had here the state space models here, and we developed something that had only a linear complexity in the computation time, and we called this the Mamba systems. But also we had convolutional neural network, and also we had vision transformer developed. So we did not just have a lot of different domains, a lot of different modalities, but we also had a lot of different architectures. And if we wanted to put everything into one huge AI system, it was getting complicating like hell. And suddenly a new idea emerged. And this idea was, can we build a modular structure? So you might say, what exactly do you mean? Well, we don't have everything in one, but we go now, hey, only a speech, so only a LLM, only a transformer architecture. We have a supervised fine-tuning that is domain-specific and valid, and we have exactly here an alignment approximation in the way that we want the system to behave on our domain-specific data. And everybody said, that looks great, let's do this. So we moved now from a single large language model here to an AI agent. What is the difference? What happened? Almost nothing. We just here formally now said, okay, our LLM has been trained to understand function calling, to initiate whenever it encounters missing data, that it said, hey, I have to connect to the internet and, I don't know, go to Google and Google this, and then I get additional data. So function calling was access to the external world, and tools were different tools. For example, access to a SQL database, NoSQL, to I don't know what, your corporate databases, your document server, whatever there was available, and also here to coding environments. And the other main difference was more or less a little bit of a local memory for our LLM. So it could remember its last steps, and it was able to remember what it has done in a session already. Plus, with this prompt engineering and everything, there was something called like a chain of thought, a tree of thought, and we tried to give this system some advanced reasoning capabilities with a little bit of prompt engineering, with a little bit of example that we provided, with some template structure that we had now in our input pipeline, and so on. Now the beauty was suddenly that, let's say we had here an AI agent that was trained here on language, and we had here an AI agent that was trained here on image, let's say here on medical image data, and here on a medical domain-specific knowledge. Suddenly we had two agents that were here really optimized for their particular task, language and vision. And then, let's say we have here the medical literature, and there's everything in there. You have textbooks, but you also have, I don't know, illustrations, you have data from X-ray data, or you have MRI data. So you needed suddenly here kind of a coordinating instance. And of course, if we're talking about agents, this was also another agent. And I call it here the general. So the general here had here its troops, and the general decided what to do. So simple. The query from the user, I had a query, hey, explain this particular medical instance to me. And the general decided, okay, I don't have it here in my parametric knowledge. I can't answer it right away. So I have to decompose here this given task, and I know I have here an access to the LLM and to the vision language MARL, and now I subdivide the task into different subtasks, and then I assign each subtask to a specific agent in a specific sequence. Great. So let's say the general decided, okay, I can have one query and three subquery. And the first is here, just go to the lexica, medical lexica, and find out everything in the data. Then have a look here on the internet for the latest literature. Then go here in, I don't know, an image repo. Give me all the latest image data that we have. And they constructed then the task. Of course, you immediately have here an idea. What is the problem? This decomposition of a given task given the available agents. But this was here the, let's call it, superior task and the superior intelligence, hopefully, from our general, that he decided how to move his troops, how to divide here the task in the subtask. Now, the more agents that are now operating in your ecosystem, the more additional problems we encounter. Because imagine we have here an agent here for the medical image data, like an X-ray chest, or we have here medical video data if you have a head MRT, or if you have here a medical simulation software environment where you have 4 particular parameters of the patient. This simulator can calculate here a specific future behavior of certain organs, of certain biological systems, whatever. So you have image, video, code, and speech. And now it gets a little bit more interesting because suddenly we have now a complex task coming down from the doctor, from a medical professional. And now this general AI, or as it's called, orchestrated AI, or whatever you like to call here, this general decision-making AI, they had to divide now this in different subtasks, knowing what kind of specific agents were available. Later, it developed that this central intelligence decided what agent to build, what agent to train automatically, and then, if you want, what agent to establish in its own network for a specific task. But let's be here in the easiest way. Let's say we have 5 subtasks. So general says, okay, I have here a main query. I go here to the LLM, and the LLM says, hey, buddy, I have no idea how to solve this, no? But I know I have access here to a medical image data analysis to interpret here a specific, let's say, X-ray chest image. Great. And then this calls here another agent, and I say, hey, look, I have here some medical, I don't know, some different perspective, or I have to do a rotation or translation invariance here to my images. Can you have here with the code here, can you normalize here, for example, here, my image distortions? Great. Comes back. This is now done here. Then come back here, says, okay, now please create a time series of this data from the simulation. So you create a medical video data stream here for this particular task, specific task. And then you come back here to the medical image data. And then you take, I don't know, every 2 seconds here the image. And then you start here also to maybe in the video simulation, another simulation. But finally, you somehow get a result. You come back here then to the language here, to our speech agent. And then this agent finally gives here the answer then back here to our general of our tropes, and the general answer here back to the human. Now you might say, hey, this looks funny, no? I mean, all questions coming down here, the pipeline here from the human, they can be real simple and they can be real complex. Simple is no problem. Simple we know, no? Complex, and on a level of complexity that a general is not able to solve, and the system will start to crash or hallucinate like hell. So here we encounter our first problems, and we have here with a communication protocol between a multi-agent AI system here, a way to optimize here that the communication structure is established and the communication structure will not become the bottleneck. I have here another video where I show you that if you have multiple agents, and I have here 7 agents, you can integrate here a further data representation. And here I've chosen here a knowledge graph. And if you want to see here this in a particular detail that I've given here from Harvard University, they developed a new knowledge graph agent. So you have a medical LLM and you have data stored on a knowledge graph, a high-dimensional knowledge representation in a graph-like structure. Then you want to probe this structure to augment your medical data. Or if you want to have the decoding on the graph structure itself, I have this video here, and this methodology was developed by MIT, Massachusetts Institute of Technology. Great. So you see, now the more agent we have in our set of agents, the more challenging it will become, and the higher the solving capabilities here of decomposing here a simple question in all the available subtasks, and have then also the dependencies between those agents in their workflow. This is not easy to do. You can have some standard approaches if you're working in a hospital. You have, okay, method 1, method 2, method 3, but then there are maybe some other methods that humans still have not developed, or there's an optimal configuration for this system, and then we use mathematical simulation models. Great. Yeah. Function call, for example, here for medical simulation data, normally you have this here in the code environment. Let's say you have some DNA data, or you have some sequence data, or whatever molecular data you have. In addition, for some specific tissue probes, you have then here with this tool capabilities to bring in this patient-specific data. Or as I showed you, you have simply a knowledge graph. If you're more oriented here on a certain population of patients, then you have here a little bit more general knowledge, and you can integrate here different sources of knowledge. You see, it is all data, but how the data is represented in a graph structure, in a database structure, in a vector space structure, in an encoded transformer structure, it doesn't really matter. It's more or less only mathematical operation to transform from one system to the other. So AI, if we give it the right tools and the right knowledge how to use these tools, AI should in theory be able to operate here even a complex system. Talking about a complex system, in this video I showed you here smart LLM routing between different LLMs and a novel multi-agent framework where, given here a multitude of possible architectures, the AI tries to optimize it itself, how the optimal system configuration for a particular data stream in a particular domain, let's say medicine, should be, and it compares this. It's a pure trial and error methodology, but the AI can build end-to-end systems if you give it enough data and enough time, and the complexity is on a level that the AI, the LLM, has been trained on, with training data on this particular complexity level. It makes no sense if the AI training data on a complexity level 3 out of 10, and the AI should solve here a complexity task 9 out of 10. Great. There are a lot of different agent communication and agent building systems out there. And this video I showed you here a very beautiful solution by OpenAI, but you know maybe Crew AI, or you go with a Mistral AI agent, or you go with any other software. Never mind, this is true for any system configuration that you might encounter. Now, real interesting, and the reason why I did this video of, oh my goodness, almost an hour. What is if you have no central intelligence that controls and commands all the agent? What is if you have a swarm and you want a swarm to develop a swarm intelligence, a specialization of each agent in the group, and the group is only interacting, but the group has no commanding structure? If you're interested here, this is the video for you. And yes, I look at nature to understand here the different methodologies. In my view, and the whole video is just my personal reflection on this topic, if I would like to summarize this, or if I am asked and I have the task to explain this, I think this is the way I would do it. Now, the question is not to create here the perfect agent population, so where to buy agent number 1 from OpenAI, agent number 2 I buy from Perplexity, agent number 3 I buy from Microsoft. No. Yeah, each agent has its particular skill set. Each agent has been trained on a particular domain. Then they work together on your task. Yeah, great. But I think what's really the challenge right now is to find the path to the most efficient solution before you start the complete process of inference. So this means that the general in the middle, do you remember this image? The general has to find here what is my best solution, given the criteria of time, money, efficiency, energy, available resources, whatsoever. This planning intelligence, if you want, this is currently, in my personal view, the most critical, the most important intelligence that we are focusing on to build better AI systems. And there is a hidden feature that you should be aware. All the different AI agent systems where you can build your agents, they have a hidden idea that you can decompose each and every task. Now, you know from logic, from physics, from mathematics, this is not the case. There are tasks that you cannot deconstruct into simpler tasks. So this works only if the task is able, the AI is able to decompose it in simpler tasks and then design here an optimal agent set with specific skills. And today, as I told you, this general can here build its own agent, its own soldier if you want, with particular skills if he has the right planning and if he understands exactly what critical capabilities each and every agent should have in order to be able to find a solution to the user query. And one of the most important aspects that everybody forgets is here tool use. And you might say, why? Let's have a look here in this video, where I showed you the perfect reasoning for every AI agent. And here on the left side, you have a logic test that I have from Stanford. So you have here condition, and these are just artificial words. There is no reason, there is nothing that the system could be pre-trained on. This is just an abstract logic test. So we have conditions and we have facts. And then the task is easy, validate a specific statement. Now you could do this in the language, and this takes quite some time, and currently only 2 or 3 systems are able to solve my extreme logic test. But if you transfer this representation of the human language into a standardized code, it becomes so much easier almost for every machine to solve it immediately. So I ask here ChatGPT-4, I think, yeah, with Canvas here to create here a logic inference solver. And you have here then simply that all the facts are just here as set. Then you have here the rules defined that were here in the human language. Now it's a simple code structure. And then you simply have a function to apply the rules and derive the facts. And you can calculate this within seconds. So you think, see, you have to find at first the right representation, the right planning. It doesn't make sense to solve this in an LLM. But if you transfer this here into abstract code, it can be solved immediately in Python, C++, in script, whatever you have, and every system can solve this. So my, if you want, idea was, whatever you have locally on a machine, and maybe it's just a 1 billion free trainable parameter system, and maybe you have a 4-bit quantization in your LoRa adapters, never mind. If you have access to tools, if your LLM has been trained to understand and use tools like a Python environment, either you go Python, you go Prolog, you go Lisp, you go Scala, whatever you like, it doesn't really matter. You are able to solve problems that you can't solve by the LLM or a vision language model alone. Therefore, LLM plus the right tool, you can solve everything. However, there's now a new development in the last 1.5 months, because you remember we were talking here about pre-training, fine-tuning, and then the DPO alignment here in the reinforcement learning. Now what we encounter is we are still hallucinating like hell. And we have now in the inference now some new ideas. So while we send off our prompt and the system is calculating on our prompt, we want now to have something like a test-time augmentation. So we want to have here an intelligence, not only in building the pre-training and fine-tuning and aligned LLM, but now also in the inference, we want to have an intelligence implemented here. And I have 2 videos where I showed you 2 different perspectives of a test-time training or a test-time augmentation or a test-time compute, whatever you like to call it. And in the first one here, I showed you, no, let's start with this one. We can have during inference here a policy model and a reward model that are now trained on your specific task, that is the input of the human. Plus, we can have a Monte Carlo tree search on this space of available solution that is now augmented with this new methodology. And therefore, if we wait, I don't know, 30 seconds now, like in OpenAI 01, this will give us here a better reasoning performance than any other model. Yeah, I should maybe have this representation of the pre-training, of the supervised fine-tuning and the reinforcement learning. Or, wait, we go here and we have a fine-tuning process happening in the inference run. So what we say? We say, listen, this system here has been already trained on some general task. But now in the inference, I have the human query, my human query. And now I know exactly what is the human asking me to perform. And now the AI says, hey, great. Now that I have the query, now I start here the fine-tuning process for myself. So I self-tune myself as an AI machine now on this specific task that is now running, seconds are ticking. And now I do not do a fine-tuning on the complete LLM, but I use here an adapter solution and I use here a low-rank adapter that then I fine-tune, I adapt here the tensor weight structure in the different layers. And then I have here an optimized LLM that is fine-tuned for the task, and then I start to solve the task for the user query. So you see, after all the training and the pre-training and the fine-tuning and the reinforcement learning and the alignment, we still hallucinate like hell, and we still are not able to really reason. So we are moving now here in this other sector here in the inference run, and we try to integrate intelligence here. Let me give you an example. From my last video, and I remember this because it is my last video, I showed you here Fireworks AI. They developed a new F1 preview model, an LLM. And I tried this out. It's a preview, it is a demo, it is a research, so careful. And what I was amazed, if you go on their platform, imagine their velocity. They calculate now 23,813 tokens per second. More than 20,000 tokens per second run through this model in the calculation. And this is amazing. So you see, on the one hand, we have a trend in AI to make it faster, faster, faster. And 20,000 token is really fast given our current state of affairs here in November 2024. However, if you look now at the task that I've given it, it was my extreme logic test. And you see here that this is from the video, so this is a continuous flow of data. You see here for a particular name, and the name is Galleria, we have a particular feature, and the feature is staff of elements. Great. And then I just said, hey, just show me the final result as a table. So I just wanted you build me a table from your result in F1. And you know what I get back? And the answer, so really a fraction of a second later, I don't have any more Galleria as if you want a person, but I have Galleria. This is hallucination happening in real time. So just ask, hey, take this data and build a table. The system now hallucinates an additional E character into the name. Plus, as you can see, the feature that belongs to this person, Galleria, is suddenly now exchanged, and the feature is now a different feature because it is a different name. This is a hallucination happening within milliseconds, and I just noticed it because I was recording the video, the performance, the run of this system. Otherwise, I would not even have noticed that there is an hallucination happening. A few days ago, I took the opportunity and I opened up my computer and allowed an AI system to take control of my computer, this computer use feature here by Anthropic. Maybe you are familiar with it. And I wanted to transfer here a financial transaction of €1. And the system had access here to everything on my computer, and it said, okay, transfer €1 from my account to some other account. And I got back, it's not possible. I don't have access to my bank account. And I said, this is not possible. You have my banking app on my computer now. And then it showed me here the protocol, and I looked, and the system hallucinated the IBAN number, the bank characteristic transfer code number, and did there a single character modification. And suddenly it was a bank not even in Europe. So my AI tried to access on my computer with my login a foreign account not even in Europe. So you can imagine those modifications here done by the hallucination of an AI, they are no problem if you say, hey, write a nice letter to my friends to invite them to a party. But if you do a financial transaction and you only have a single character in your IBAN code different, you're gonna look like an autobus. Great. This is what I call hallucination, and it happens every time. And please, this is not F1 preview. This is not only happening on the Fireworks platform. This is happening in every single AI system on this planet. Great. Let me show you something else that is happening. And just because I did this video, it's so clear in my mind still. The same task, no? And there were 14, 15 conditions. And here one of the conditions was here, the tome of secret is not held by the wizard from Avalon. Never mind, there's nothing to understand here. This is just a logic test. So, the tome of secret, not Avalon. Great. This is here the AI F1 preview. And please, this is not on fireworks. This is valid for all systems. This is just here documented because I did it yesterday. So I have here the tome of secrets. Yeah, beautiful. And F1 preview tells me not held by the wizard from Avalon. This is correct because my instructions were not held by the wizard from Avalon. In the next sentence, this system writes, correct. Avalon has the tome of secrets. Can you explain this to me? For me, personally, that if you have not held in the next sentence, correct, it has it, is just what I call another hallucination. And then in the final verified result by the system, and I ask for multiple verification, then Avalon has the tome of secrets, although it is in the instruction, and the system understands that the instruction is not held by the wizard from Avalon. So the system just ignores data, the system just ignores fact, and the system just hallucinates whatever the system hallucinates. So therefore, be careful and be aware of these current limitations. Because what we achieved here in my last video, if you want to see this, I had an amazing platform with fireworks. I had a speed I never experienced in my life with 23,000 tokens per second. Throughput amazing. But it was hallucinating. It delivered the wrong result. So what is the use in all of this to accelerate our existing models if the result and the feedback that we get is wrong because the systems hallucinate? So, new trend, new chapter. Okay, and yes, I got a question from one of my subscribers and says, hey, what I don't get is this trending in test time compute and whatever you call it, and it seems to bring a sort of plasticity during inference. Okay, beautiful question. Let me explain this. Why we have this focus now on inference? Why do we think we are more or less here, everything is experienced here? Why we are now moving here to test time training? To jump over this famous wall that is happening. So what we want is now, we don't want speed and the wrong result. We want slow and the right result. What does it bring if I have 20,000 tokens that are wrong? So I wait now 90 seconds, 120 seconds, 150 seconds for OpenAI O1 system to generate an answer for me. So you see, complete reverse the trend. Because now in these 90 seconds, my OpenAI O1 inference can now optimize here the policy model and the reward model for the reinforcement learning for my specific task during my inference run on O1. And you might say, but the system should be trained on this, no? Yes, it is trained on the general idea of a task, but my specific task in my wording, with my data, in my complexity, was maybe not in the training data set, and therefore the machine must now optimize itself to bring itself into an AI configuration that it can solve my specific task during this inference of 90 seconds or 120 seconds with OpenAI. And those are exactly here from those two videos, two methods that I wanted to show you how to do this. Either you focus here on the reinforcement learning with the optimization of the policy model and the reward model and the augmented search base, and you have the advanced Monte Carlo tree search algorithm, or you go on the fine-tuning, you see this one here, and you build your LoRa adapters that are activated and trained during the inference run for a fine-tuning process given my specific task. And this adapter is only for my task. So, general model for general task. Now we focus here on this task-specific ideas. So I hoped I've given you here an answer to your question. Because, I can start now to fine-tune here a LoRa adapter for a specific task during inference. Everything is now task-specific. So the system really in the inference run of these 90 seconds tries now to adapt to my personal query. So there we have it now. We have now task-specific action happening in the inference run, and all the training is happening before the inference run. You could see this theoretically from a different perspective. If you say, I understand what he's trying to tell me. You know what? I have an idea. Why do we have hallucination in the first place? All the current literature indicates it is because the pre-training data are not coherent or are not vollständig with the supervised fine-tuning data. So this means I have a pre-trained data and either the data quality is not good or I have contradictory statements in the pre-training data. If you copy the internet, you have people say, hey, this will be the best president of all times. And you have people who say, maybe he's not the best president of all times. So what the AI should take now as a true statement. So the quality of the pre-training data, but the coherence of the pre-training data with the supervised fine-tuning data set is extremely important. Plus, whenever we try in the alignment phase to force the model to behave in a certain way, that a model, now I use here some human words, does not understand, that the model is forced to do, but there's no freedom anymore for the AI model to move or to transform or whatever, then this is exactly the case where this hallucination happens. So incoherence, if we have step functions from the pre-training data to the fine-tuning data, if we have domain shift happening in those three elements, all of this seem to be here the main cause for hallucinations. But if you build your AI system knowing what you want to use the AI system for, let's say you are in a bank office or you are a medical doctor or you're in a hospital and you say, listen, I don't care about a French poem from the 16th century. I want my AI system that I will build from scratch to be able to use all the data, the medical data formats in my hospital that my staff has. I want to use all the softwares that I have in my hospital. I want the AI is able to understand how to run the system and only those systems and nothing else. Then you can design your AI for a set of tasks in your hospital that you know you're gonna use it. Because then this AI becomes a very specialized, let's call it an expert AI, that has a coherence pre-training data set with a coherence fine-tuning and a coherence, if you want, alignment phase. Because we are on one domain for one application for one set of users, medical doctors or nurses or assistants or whatever. And you don't have to write a nice letter and translate it in 15 languages. You see, expert AI, because here we hope now that the hallucination reduce significantly. So there you have it. If you want a short summary, we have today, I think, two main ideas. The global corporation on this planet from Microsoft to I don't know what, they have this idea to have one monolithic global AI system. So we have somewhere a data center with 1 million Blackwell GPUs from NVIDIA, and this monster AI will solve for, I don't know, 100 million users all their problems from medicine to lyric and French poetry. Or, and this is an idea that I would like here, is we have a global AI system where we have a lot of, if you want, specialized, expert, dedicated AI system that are connected for a specific task, maybe for a specific region, maybe for a specific financial structure, for a specific economic structure, for a specific infrastructure that is available, whatever. But if you want, we have more or less a global network of AI agents. It is, I think, especially if you have new data and you want to train, for example, here only a visual medical node. You only have to train this node. And you can do this because it only costs you, I don't know, $100,000 and it only takes you a day. If you wait to do an update of the monolithic global AI, well, you wait 2 or 3 years. So this is not a question, what will be the future? Now, of course, our global corporations say, hey, if we have one machine for all the users on this planet and we can dictate the price, this is great. Because imagine, here you can choose your provider. No? Here you are locked in the ecosystem, so you understand how this works. Great. I was asked by my subscriber what I mean with AI. Okay, it's a highly intelligent question, and I try to be able to come up with a solution. So, at the very beginning of times of AI, we had AI simply meant here in the beginning a large language model. Then, with AI, I meant a language model with the ability of a function calling, so can connect to the internet, can connect to the weather station, can connect to a database. Then, with the advancement here, I meant AI and LLM with the function calling, plus a local memory. So the AI memorized its own operation and said, hey, I know this in addition, and you had a local log system. And then, if we added some chain of sort, some reasoning, some context system, we had an LLM with the function calling, with a memory and the reasoning. And then there was a general agreement, maybe we could use and call this an AI agent. An AI agent is because we have an LLM, so an artificial intelligence system. If you just call it an agent, you can have a rule-based agent. Then I define in Python some specific rules, and then the agent, the intelligent, is now rule-based and not AI-based. Great. So when I was then talking about AI, I was talking here about an AI agent that interacts with another AI agent and is a multi-AI agent system. And we have the MARL system for the reinforcement learning, training, and so on. Now today, if we have the LLM plus the function calling plus the memory plus the reasoning plus, as I told you now, in the inference run, the test-time augmentation, this, if you want, call it an AI agent star, like Q star, A star, no, A star would exist, an agent star. And now if I talk about AI today, I mean an AI agent star interacting with an AI agent star with a test-time optimization and memory optimization and reasoning optimization and function calling to tools and a tool optimization and an LLM optimization in the pre-training data, in the fine-tuning data, and in the alignment data. And then I have a multi-agent star configuration, and then the intelligence now in the interaction of those AI agent star. This is today what I mean with an AI agent system. And if tomorrow we develop new technology, it will further develop. Of course, the same is true. You see, I always talk to you about large language system, the vision language system, the video language models, all the audio systems, everything that is coming next. So whatever you have, this is the general trend that I currently see in my simple mind here. What is happening today in AI? And you might sit back and say, I'm so glad that those folks, they didn't enable here the AI systems to self-improve, Imagine this AI system would self-learn. Because maybe currently we humans, we are not really currently in the mood to self-learn at 110% capacity. What would happen if those systems start to self-learn? Well, interesting that you ask, but now I have here this video, and this video you can find, it's called How to Build Skynet. This means Adaptive Multi-AI Agents. And then in this video I explain to you how to build adaptive AI agents with specific configured action spaces for specific tasks. So adaptive AI, where we have a self-adaptation of the AI system given a task and a self-configuration of the system. This is here the next step, so if you're interested, why not have a look? In general, this video was quite an unusual video for me because I've only given you my personal view on this topic. If you see here, normally I have here in my videos, I talk about here NVIDIA developments, or I talk here about new test-time optimized reasoning methodologies and algorithms developed by MIT. Or I show you here what our friends in China here, Changyou University, they have here test-time adaptation and. So if you're interested in, if you like this style, here's your subscribe button if you want to see me in your next video.